So for this function generator, this is pretty easy to use. This is the power button. So you press it, you turn it on and off. This is the mode. The mode will allow you to go between different kind of functions. This generates sine functions, square functions, triangle functions, etc. If I change that to square, let's see if my display looks like. The display is not. Oh, I have to press the run stop button for it to actually produce a signal. And so you see a square pulse. So if I turn it off, I can change the mode from square to triangle, and you see a triangle. Turn it off, I change the mode to sawtooth, I get a sawtooth. Change it off, etc. Okay. Pretty straightforward. And then the cursor on here allows you to change the frequency. Let me change the mode to sine function. Okay, the cursor allows you to change to different values so you can change the frequency. Don't use very high frequencies, just stay between, we're going to stay between 1 and 10,000 hertz. For this lab, I'm going to have you choose, because it says in the lab, I'm going to assign you a signal. You can just choose your own signal. Choose your frequency and choose the shape of the signal and choose your own voltage. Okay? So with the cursor, with the plus button, I can actually change the value of the frequency. Let me go change the frequency to 2,600. Down is, the minus sign goes down, the plus sign goes up. And then this starts it. Okay, the run stop starts it. You can't change anything on here until you hit stop here. There's a filter here. It's a low pass filter. Haven't figured out the effect of it. Haven't been able to see the effect of it. I've actually gone online to look at if anybody can describe the effect of that filter. No one knows what it does. Okay, which is kind of strange. And then there's a DC offset. And what a DC offset does is allow you to basically adjust I think I got too much voltage on here. It'll adjust the positioning of the signal. It puts an offset in your signal. We're not going to be using the DC offset, so I wouldn't worry about it. Just leave it off. Okay. All right, I'm not sure why it's cutting it off. Okay. That's pretty much it. All you need to know how to use is the mode, the cursor, the plus and the minus, and the run stop. You don't have to worry about the filter. Then, of course, this to adjust the height of the signal. Okay. How do you change the voltage? This button right here. This says amp over here. And then that changes, basically you're changing the amplification. And you probably don't want to crank all the way up, and I had it cranked all the way up. So let me change my voltage per division right here. Okay. Now this scope does display a lot of stuff on here. You can use it as a check, but I want you to measure things. Because I don't know how accurate some of that stuff is. The earlier class, I had the signal generator set to 1600 hertz, and it was telling me it was measuring 1700 hertz. I would actually go by measuring the signal on here. So normally what I do is to make measurements, I try to make the signal large, so I try to spread it out as much as I can in the horizontal direction and also in the vertical direction. Because I'm going to be measuring vertical and horizontal distances to measure my time and voltage. The bigger the distance is, the better precision. Does that make sense? So you see a grid on here. All scopes have a grid. Let me go back and change to the the document. Not that document. Sorry. This document. So you see a grid there. On the scope that you would use in the lab, each grid is a centimeter, and each division is a centimeter. So each box is 1 centimeter by 1 centimeter. And then there's 5 divisions in between each centimeter, typically. Our scope doesn't go by centimeters, you just call them divisions, okay? But typically the ones on the oscilloscope that you would use in class, the boxes are 1 centimeter by 1 centimeter. Ours are the ones we're using are not, because the display is so tiny. Okay. Then the divisions, there's 5 divisions in between. So the question is, in terms of sig figs, how many decimal places can I measure distance? And I would say you can't measure to better than 1/10 of a unit. So if one box is 1 unit, you cannot measure better than 1/10. And the reason why I say that is because the display, also called a trace of the signal, right? The display, the voltage versus time that you see, the graph, is called a trace. That trace has a thickness to it. Its thickness is about half the spacing between the 2 closest divisions. So to say that you would be able to measure something to the 100th place, just to me doesn't make sense. So let me go on the board and let me describe. I'm not going to draw the whole grid, because if I draw the whole grid, everything is going to get confusing. And then the grid has to be equally spaced. I have a hard time making it equally spaced. Okay. So here's my coordinate system. This is my origin. I'm going to draw some arbitrary signal. I'm going to draw like this. Okay? So I'll draw my signal in that manner. Now again, the vertical direction is volts, the horizontal direction is time. So on the vertical axis, I can measure the distance from here to here. So I can actually measure this distance in terms of the number of divisions. Like I said, on a regular scope, that's going to be in the number of, it's going to be centimeters. Let's say that the height from here to here, from the upper peak to the lower peak, called the peak-to-peak voltage, this distance is 3.4 divisions. Okay? Let's say I measure this to be 3.4 divisions. Of course, what you want to do is you want to adjust this signal so that maybe the bottom here is along one of the grid lines. You can always adjust the signal up and down so that this thing is along one of the grid lines. That makes the measurement a lot easier. You don't want it to be in between grid lines. You can actually move this all the way up so that this point is over here to make the measurement easier. You can shift this up and down. You can shift this left and right, just so that you can make easier measurements, or to make the measurements easier. Now, how many volts does this correspond to? It just says divisions. So that's going to depend on the scale you're at. You can change the scale setting on the scope. In the case of the CRT scope with the electron beam, is going to basically changing how much the electron beam deflects from this point to measure voltage. In the case of, if this was an electron beam, it would be scanned across the screen, the electron beam. And when it hits the screen, it's going to, the screen's phosphorescent, you see a green line. And it scans it very quickly. Okay, so let's say the vertical has this knob that you adjust. And let's say you adjust the scale so it says 50 millivolts per division. Well, if it's 50 millivolts per grid, the big box, and I have 3.4 boxes, then the voltage I'm measuring is going to be, I'll use black so you can see it better, is going to be 3.4 divisions times 50 millivolts per division, and that ends up being 170 millivolts. And like I said, you're not going to get more than to the 10th place here. So this number is 2 sig phase. This number will probably have no more than 2 sig phase. Okay. I would say that this is 3.4 plus or minus 0.1 divisions at best. That's why I'm saying, if you're going to measure voltage, expand this in the vertical direction as much as you can. That way you'll get more precision. Because this number is never going to change. It's this number that's changing. So you're always going to be able to measure 0.1 divisions. They just make this bigger and you get better precision. Does that make sense? Same thing with time. So right now, this is really a number 2 sig phase. So I'm going to estimate, I'm going to guess that this is 170 plus or minus 10 millivolts. Of course, if I do air propagation, I'll get a better value. Now, what about the horizontal? I have it back inside. What I want to do is measure the period of this signal. So I measure the time it takes to go from 0 to 0 to sweep across. I want to see when this thing repeats itself. Let's say this is 5.1 divisions. There's a knob here for the time scale. The seconds per division. Well, let's say that you set the time scale to 10 milliseconds per division. And this is 5.1 divisions. So then I would take 5.1 divisions. Wow. Times 10 milliseconds per division. And this ends up being 51 milliseconds. So it takes 51 milliseconds for this signal to repeat itself. And so the frequency, so this is the period. The frequency is 1 over the period. 1 over that 51 milliseconds. Actually, if I did that in my calculator, this would end up being 19.6 hertz. This is all I want you to be able to do in your video. That's it. I want you to be able to put a signal on your scope, tell me the voltage, and tell me the frequency. Now, you can compare your frequency to what's on the signal generator. Let me put the signal generator. Right? You can compare it to what's on the signal generator, but also the scope does display it. But I don't know how accurate that display is because it uses some averaging technique. Okay? So you can actually compare your measured value to what it says on here. So when you do the lab, set this to a nice value. Yeah, just good question. It will be on the screen. So at the bottom of the display, I'll go back to it in a second. At the bottom of the display, it'll tell you what the scale setting is. Okay, so you will know it. Okay, you will know what all these are because it'll display it to you. So all I need you to do is to be able to put a signal on, pick a signal, pick a nice number for the frequency. Don't pick 300 hertz because the reciprocal of 300 is not a nice number. Pick 400 hertz. Pick 4,000 hertz. or 800 hertz or 8,000 hertz, because the reciprocal of those numbers, you don't get a repeating decimal place. Because you're gonna get the period in the frequency. So that way you can compare it to what your device is. And they're pretty good. Okay, actually, there's a way to calibrate these scopes. It produces, the scope itself has a little notch on it that produces a 1 kilohertz signal, and you can use that to calibrate your scope. That's typically how you calibrate a scope. You actually put a 1,000 hertz signal in it and make sure it reads 1,000 hertz. So it does have a standard in it, so you can calibrate it. But when I tried it, when I checked it out, it was pretty good. Okay. But what bothers me is the numerical displays. I don't like the numerical displays. I don't think they're that accurate. Okay. So let me go back and show you the scope again, so you can I can answer your questions better regarding the display. Of course, I got to switch again. Oh no, I'm okay here. Let me just switch to the. All right. I'm going to move my. So at the bottom here, and it's not very clear. Let me get my camera real close. Sorry. That's the bird. You see where it says 50 milliseconds in the box? That's the time scale. And you look at the left where it says 1 volt. That's the voltage scale. Okay? Sorry, it's going to make me, it's kind of dizzy doing that. Sorry about that. Okay? So you can see that at the bottom, and then I'm going to talk about the triggering in a minute. So you can see that all at the bottom here, and you can change it. You just change the, this guy is rotated, and you can see the numbers change. Same thing for the second one. You can scan through it. Okay. This is not the ideal scope to use. The ideal one really for us to use is this one, because it has 2 inputs, so you can compare the power supply voltage is whatever you're measuring. You can look at shifts in your voltage, etc. But we're going to go with what we can get. So, all right. So let me talk about triggering. You can tell the scope when do you want it. You can tell the scope when do you want it to start measuring the signal. You want it to measure here when the signal is going down, or you want to measure here when the signal is going up. Let's call it triggering. So there's 2 kinds of triggering. There's a level triggering, which tells you what voltage you want it to start triggering. And then there's edge triggering, which tells you you want to display when the signal is going down or when the signal is coming up. When the slope is positive or when the slope is negative. So there's 2 types of triggering that we have in the scope. And then there's 3 modes of triggering. One is called auto, which basically doesn't really do anything. So if you have a messy signal, your display is going to be a mess. There's something called a normal mode, which means that if you set your criteria for triggering to certain values of the voltage and the slope, the scope will wait until those criteria are met, and then that signal is displayed. That gives you a nice clean signal that you're looking at. And that works well if you're doing signals that are not very high frequency. And then and for the cases where you're just looking for a particular signal out of something complicated. Okay? It'll allow you to see that. For us, the auto will work fine because our signals are going to be clean. Generally, they'll be fine. But if you have trouble observing your signal, you can always use the normal one. And then there's a third mode called SINGL for single. Basically, it just takes one snapshot and that's it. You're done. Okay. And that's described in the handout and regarding our scope. But also the main handout talks about triggering also. So I would like for you to read the page 4 of the manual for the scope. Because the other pages are telling you how to build it. Because these scopes, you can buy it in DIY, you have to put them together. Okay, we bought it already put together. So page 4 is what you want from the manual. So read that. Then there's this document, the document for the lab itself, read that. And then I created my own document giving you the instructions on how to use this device. So let me change views again. And that's all here. Okay, so basically it's like 5 pages of reading, that's about it. Okay, or 6 pages, whatever it comes out to be. So this gives you some, hopefully better instructions than the manual. Then the second page, I actually wrote some instructions for the function generator. It's pretty easy to use, the function generator. Any questions? Let me go back to the other document. Not that one, sorry. If you go to the last page of this document, it tells you your assignment. Basically, in your assignment, you're going to create a video showing me that you know how to measure the frequency and the voltage of a signal. That's it. You'll show me the signal display, and you tell me how you make the measurements. Normally, when we do this in class, we use a tuning fork, and then we have you measure the signal from a tuning fork, but we can't do that here. Okay, so you need to fill out this form. You can always upload it with your document, or if you make in your video that you create, you can actually just display this document filled out. That way you don't have to upload it. Okay, so I just need to see your face in the video with you showing me that you know how to make the measurements. Just make sure it's as clear as possible. I don't expect it to be longer than a minute, but I could be wrong. Let's hope it's less than 2 minutes, okay? But some of the previous labs, the videos were quite long. And that makes it easier for me to download if you upload a video from Canvas. Questions? It is very important that you learn this, because you won't be able to do the last 2 labs if you can't do this lab. And most people can figure out this lab pretty easily. Okay, it's pretty straightforward. You just got to play with the scope. Okay. Questions, concerns? No concerns? Everybody's quiet today. Okay. So what I want to do in the remaining time, I want to go over the problems I skipped in lecture. There's 4 problems I skipped, and I want to do them all. What is the gauge wire? That's a good question. I can't remember. Morgan, because Tyler orders them. I think it's 14 gauge. I'm hoping you don't need any. I mean, if you run out of it or something, just let us know. Okay. You might not need all 400 for the magnet. But if you think that your magnetic field is not sufficiently large, we can have you contact Tyler. Tyler's on campus Monday and Wednesday. I do have some wires, so if need be, I can give you mine, and I can give you some of mine, or we'd have to meet somewhere. Okay, that's what I've been doing with other students if they need stuff like this. So if you don't think it's enough, if you try it and it's not really working very well, then I'll try to get you more magnet wire. And then that thing's easy to wind anyway. So I email Tyler first. If not, then email me. Okay. All right. Let me change the display. Actually, that's not what I want to do. 1 second. Sorry for the blank display. Okay. So I want to do a couple of examples. Now, one of them is a long example. I just like doing it. Okay. And I hope, sometimes when you give a more detailed problem, hopefully it helps understand the concepts. But anyway, it's not this one. So I have a long current carrying wire. It's near a rectangular loop. I want to calculate the magnetic flux through the loop and the induced EMF if the current's time dependent. Okay. So let me set this up on the board. This is really kind of a typical problem that you see in the textbook. There's not a lot of problems like this that are actually easy to integrate. A lot of them, the integrations are very difficult. Let me draw my wire. And then we'll draw my loop below it. And there's a typo there. The I2 shouldn't be there in the picture. Okay, the I2 shouldn't be there in the picture. I copied it from one of the other problems I did in the previous chapters, and I forgot to get rid of the I2. So this is a loop of wire. Now, if you have a long wire, if the magnetic field produced by the wire is mu naught times I over 2 pi r. Now I'm going to define my coordinate system this way. This is x, this is y, and I'm going to say down is positive. I just don't want to deal with the minus signs. Okay, I'm going to define down as positive. Well, that's my coordinate system, and then the magnetic field depends on the distance from the wire. Really, this should be a letter Y. I'm going to write it into Y. And the direction of the field here is going to be into the board. Because if I use the right-hand rule, I point my thumb in the direction of the current, my fingers curl into the board. Are we okay so far? So I want to calculate the flux through this loop. So this is going to be the integral of B now my normal to the loop is ambiguous because I can make the normal to the loop either point towards us or into the stream. I want to make the math easy for me. I don't want to deal with the minus signs. I'm going to choose and move to the board. What that would mean then is if I were to calculate the integral of E induced dot dl, just to be consistent with the right-hand rule, if my thumb points into the board, I'm going to be integrating clockwise. Okay? With my thumb pointing in the board for the normal, I would be integrating clockwise. My DL would be clockwise. And of course, I would assume, because I don't know the direction of V, I would just assume E is clockwise. If I'm wrong, I'll get a minus sign out of it. But I'm not gonna, my goal is not to figure out E, but I'm just telling you the reason why I chose the normal to the loop so that the dot product between B and the normal is 1. The dot product gives me a cosine of 0. Cosine of 0 is 1. So then I can just do this. Okay. But again, if I'm doing that, then that would imply that when I do the integral of E dot dl, then I would be integrated clockwise. Okay. What's my dA? I know that the magnetic field decreases in this direction, but it doesn't decrease horizontally. So I can break this up into areas that are small enough so that the magnetic field is constant over that strip. So I'm going to make a strip here of thickness dy and length L. The magnetic field across that entire strip is constant. Oh, you want me to explain? I'm sorry. Let me finish my DA and then I'll get to your question. So my DA then is LDY. Again, the magnetic field over that strip is constant. I want to break this up into small enough sections, areas, so that the magnetic field is constant over that area. So that's what I did. Now, regarding this question, I can choose my normal to the loop either into the board or out of the board. Isn't that true? It's ambiguous. Right, Morgan? Because it's an open surface. However, if once I choose a direction, into the board, then I'm also choosing a direction for which I'm going to do this integral based on the right-hand rule, which you would see, you don't see it here, but you would see it in Calc 3. All I'm just stating that once you choose the direction into the board, then I'm choosing the direction in which I'm going to integrate this. Okay, that's why it's important. But I'm not going to do this integral. Okay, I'm not going to do this integral. I'm not interested in E there. Does that answer your question? Yeah, I can't give you a clear, I mean, this is related to something called a curl that you learn in Calc 3. It's related to some sort of cross product, and all cross products obey a right-hand rule. Okay? So that's all I can say from here. So this involves something involves a cross product, and anything involving a cross product involves a right-hand rule. And so when I choose the direction of n, I'm choosing the direction in which I'm integrating. But like I said, I'm not going to do this interval, so I don't care. I just wanted to say that. Okay. All right. So my dA is this. So I put that in dy. What are my limits of integration? Well, this is d, and this is d plus a. And I chose down to be positive, so then I'm going to go from d to d plus a. And so this integral is easy. Let me write it down here. Now, the induced EMF is minus d phi over dt. As long as the current I1 varies with time, then I will have an induced EMF. Because then I have a changing flux. If I doesn't depend on time, I don't have a changing flux. Well, let's assume that di1 over dt is not equal to 0. Then if I want to find delta V induced, then this is going to be, if I take the derivative of this with respect to time, the only thing that depends on time here is the current. That's it. And if the di dt is bigger than 0, the induced current will be counterclockwise. If di dt is less than 0, then the induced current will be clockwise. Oops. That's a screw up on my part, sorry. Thank you for pointing that out. I don't know why I put an N here. I'm thinking of solenoid for some reason. I got the solenoid in my head, sorry. Okay. We okay there? We okay with that problem? Okay. The next problem I want to do is the rail, not the railgun problem, but the wire on the rails. So let's say I have a set of rails with a magnetic field into the board. And I put a rod on here and the field's all everywhere. Okay, I didn't want to draw the field everywhere. I gave the rod some initial velocity v rod. And in the example we did in class, we know that when we give that a push, that there's going to be a force on it to the right. There has to be. Because when this thing moves to the right, a current is going to be induced in my loop. And I don't show the right end, I don't show the left end there, but there's going to be a current that's induced. So the mechanical energy gets converted into electrical energy. This has to slow down. That means there has to be a force in the opposite direction. And just from that, we can deduce the direction of the current. But we saw in class this morning that the direction of the current is upward. Okay. And I use I sub n for motion on that. The question is, can we figure out the velocity of this rod as a function of time? Well, I know that the motional EMF is B times the length of the rod times V of the rod. I know that the current that's induced because of this motion is B times L times V of the rod divided by its resistance. Okay. And using the equation, F is I L plus B that we learned in chapter 29, then the force on the rod, at least the magnitude of it, is I sub m L B, where I sub n is this. Okay? So that's the force on the rod. And it's opposite the direction of motion. And so let's pretend there's no friction between the rod and the rails. Let's pretend also that see, my rod looks like it's cylindrical. Let's just assume it slides. Okay? I don't want it to roll because that adds a complication. Which is solvable, but I want to deal with it. Okay, so we have a force of B times L. In fact, if I combine these, I get B squared L squared. V rod over R. Let's equal to MA. This is opposite the direction of motion, but A is dV dt. So I can rewrite this and divide both sides by m. This is a capitalized, sorry. Now, I'm going to isolate the v's on one side. Okay, let me isolate the v's on one side. I'll get to your question regarding the v decreasing. So the question was, how do I know that? A couple of questions. Number one, how do we know that the velocity decreases? And we made this argument this morning. If the velocity increases, what happens? If I give it a push and then the thing accelerates, what does that mean? I mean, I violated the law of conservation of energy, which is impossible. That's number one. Number two, when I give it a push, this thing has kinetic energy. But then electrical energy is produced. Where does the energy come from? It comes from the kinetic energy of the rod. Okay, sorry. Okay, does that answer why the V decreases? It has to decrease. It cannot increase and it cannot stay the same. Because we have to obey conservation of energy. Now, what is the R? What's the resistance of the system? Okay? All right, current is voltage over the resistance. We're assuming there's a resistance in here. Just like the problem I did this earlier. It's the resistance of the whole loop. Whatever it comes out to be. Did I answer both of your questions? Yeah, what I said earlier, there's a loop all the way at the end. I didn't draw it. There's an end to it. I just drew part of it. I just assumed it was very long. Okay. I didn't want to draw the whole loop, but it's there. It's there. It's somewhere really far away. And if you want me to, I'll do this like a break. Because what people write. Okay, but there is a complete loop there. I just didn't draw the whole loop. I didn't want to draw the whole thing. And this is supposed to be really long because when I solve the problem, you'll see that the velocity goes to 0, t equals infinity. Okay? So there is a loop. I just don't show the whole loop. Okay. So yeah, I screwed up there. I should put it here. So now let's integrate this. If I integrate this, then I get some constant minus b squared L squared over mr times t, and that's equal to the natural log of the velocity of the rod. Now, exponentiate both sides. E to the c is a constant, so I'll just call it d. I know if I call it c, you guys won't be happy, but I'll just call it d. Just a constant. What is that constant? Well, that constant is the velocity of the rod at t equals 0. So in principle, t has to go to infinity for the velocity to go to 0. Of course, that assumes there's no friction. There is friction. Okay. There is friction in the system, but I idealize it. We okay with that? Yeah, I apologize if I don't show the whole loop, but I don't want it's supposed to be very long. Okay. So I have two more examples I want to do, and I want to do the easier one first. I didn't do this with the other class, but I want to do the harder one last. So the problem I want to do is the following, and I'll come back to the easier one, or the harder one. So we talked about the back EMF. Oops. We talked about the back EMF, and I want to just do an example. It's an easy example. There it is. Okay. So when a motor is running, let's say at 120 volts, when it starts up, a back EMF is introduced. And that back EMF produces a current in the opposite direction that's produced from the power supply. And that actually really reduces the current in your motor. So if you have a motor, the current in the motor from the supply is just delta V over R. If you have a back EMF because of the motor, then you're going to have a current in the opposite direction. And then they use the script E. This is traditionally what's used. This is the back EMF divided by R. So that the total current then, the total current drawn by the motor is delta V of your supply minus the back EMF over R. So if you have a drill, and when you press too hard on it, you'll notice it overheats. Because it's not running at its normal operating speed. It's drawing more current. When it draws more current, it produces more heat. The more heat that's produced, the hotter it gets. Drills don't like that. So let's say we have a motor that runs at 120 volts, and it's 4.1 ohms. When it starts out, it's drawing 29 amps of current. But this thing goes down as the motor speed increases. And there's a back EMF of 118 volts introduced. So what's the total current that I get? Well, it's going to be 120 volts minus 118 volts over 4.1 ohms. You go from this value to this value. Now, this is, I think, a little bit exaggerated. I stole that out of a book. It just seems very exaggerated to me. I just want to remind you is when you have a generator and there's a load connected to the generator, that means there's a current running through it. That means there's going to have to be, you have a rotating loop of wire in a magnetic field, there's going to be a torque on it. The magnitude of this torque, this is called counter torque, is going to be the magnetic moment times B times the sine of the angle between the area of the loop and the magnetic field. And generally then, this expression is going to have, this guy will have a sine term in it, and so will this term. You'll end up with a sine squared term in it. You have a homework problem where you're actually going to look at the counterpart. They're pretty straightforward problems. The only hard problems in the homework are the last two. Okay. The only hard problems, really, challenging problems in the homework are the last two. Okay, so I'm getting towards the end of class. If you don't have time, I understand. I want to work on this problem. I did it with the other class. It's a little more challenging problem. It's a problem from your book, but it's a Faraday's law problem. Let me go back. This is a rail gun. Where I have to draw the whole loop, okay, in this particular problem, because I have to show you where the power supply is. This is a rail gun. I guess I didn't need to show the right end of the loop, but I close the switch in the rail gun. Let's say it's really long. If you guys don't have time, you guys can leave, that's fine. I'm still recording this, so. So I have a power supply, switch, let's assume this is really long, and it ends somewhere down there, whatever. You want to draw the loop, go ahead and draw the loop. But when I close the switch, and they have a current running through there, through this rod, because of the fact that I have a magnetic field into the board, and the current's going this way in the supply, that's going to produce a force in that direction, the force into the supply. Just use a right-hand rule. And so the force into the supply is I sub s, if this length of the rod is L, times the external magnetic field. But guess what happens? What happens as I go in this direction? I have a changing flux. Okay. And so I'm going to have an induced emotional current. I'm going to have an I sub n here. That's going to produce a force in the opposite direction. This is causing it to accelerate, this is causing it to slow down. What is the overall result? Well, I draw a free body diagram. There it is. Let's pretend there's no friction here. Okay. By the way, you have a problem in the book where you actually consider the EMF in both loops. You see that. Okay, so the total force on this thing is going to be I sub s times L times B minus the motional EMF times L times B. And that's going to be equal to MA. But this is dV dt. But what's I sub S? I sub S is the power supply voltage over the resistance of this loop. Okay? Or if this is big enough, it's going to be the resistance of that guy. However you want to look at it, but it's just the resistance of the loop. Okay. So I guess that's probably a good way of thinking about it. It says the voltage. Then L and B. Now what's I sub N? Well, I sub N is the induced EMF over R, which is B and L is V rod over R. So let me rewrite this as delta V sub S times L times B over R minus E squared L squared over R V rod. Let me divide both sides by the mass of the rod, M. Let me clean this up a little bit. Let me factor out this LV over MR. Now where do they go from there? Well, I have V on here and a T on here, so I'm going to put all the T's on one side and all the V's on the other. And then I'm going to integrate this thing. Integrate both sides. So what do I get when I integrate both sides? I'm going to get L, B, over M, times R, times T, plus a constant, equals the natural log of delta V sub S minus B, L, V rod. Sorry, I'm running out of space. Oh, and then I forgot, I get a 1 over the L here. Let me multiply both sides by B times L. My goal is to solve for the velocity of the rod. Oh, yes, you're right. There's a minus sign. Thank you. Okay, thank you for that. There's a minus sign. Okay. Can I put the minus sign on the other side? Okay, let me put the minus sign on the other side. How's that? Oh, now look, C is a constant. Aren't B and L a constant? Can I just call it D? Is that okay? Are you guys okay if I just call this thing a constant D? No one's gonna oppose me. I mean, no one's going to object to it. It's just a constant. Okay. So let's put b there. I'll leave the minus sign there. It doesn't matter really. And guess what I'm going to do next? I'm going to exponentiate both sides. When I exponentiate both sides, I get e to the minus b, which is a constant. Okay, e to the minus d is a constant. Can I give it another name now? Can I call it k? Let me just call that k. Okay, it's just a constant. In the end, I'll figure it out. I gotta erase this. So I want to solve this for b rod. So I'm going to move this to the other side of the equation and divide both sides by minus bl, sorry. So I'm going to get the following. Question is, what is k? Well, v rod equals 0 at t equals 0. So, k has to be equal to delta v of s. So that means, I'll make sure you guys can see this. That means that our equation looks like this. So, what is the velocity when t goes to infinity? Where's the velocity of the rod when t goes to infinity? Well, this thing goes to 0, the velocity of the rod is just this. What do you call that velocity? The maximum speed it's going to reach. What do you call that? That's a terminal velocity, right? Yeah, it's a terminal velocity. So v terminal is delta v sub s over b times L. Because I did all that work to figure it out. I can go over here and figure that out. All right, because I can set this equal to 0, and I'll get the same expression. Right? Because if I take this expression, I'm not going to call this v terminal. These two cancel, the r's cancel, I get delta v sub s. I get that. They should agree, right? I mean, they should both agree. But this is 0 again because acceleration is 0, it means the terminal velocity. We did have our engineering club one time wanted to build one of these, but they require a huge power supply. So they weren't able to do it. There's a lot of heat generated. And of course you end up with a very fast projectile, which is dangerous. Any questions? I'm sorry I went a little bit long. Hold on, okay, let me go back here. What? Which V are you describing? Are you talking about this V? The V sub S is the power supply voltage. This is the supply voltage. This is the terminal velocity. So basically what I said was, here, where's the velocity at t equals 0, at t equals infinity? We call it the terminal velocity, so I changed the v rod to v sub t. And it's written in terms of the power supply voltage. Okay. Yeah, no, there's a lot of v's. And there's a lot of constants there. I give you one value of it. All the constants, I just focused on the last constant. Okay, so regarding the lab, the oscilloscope quiz shouldn't be too bad, this oscilloscope quiz. Oh, question. Yes. Yes, Morgan. L is the length of the rod. I've been trying to really kind of do it the same way as I did the other problems. L is the length of the rod. B is the strength of the field. And V is the voltage of the battery, V sub S. Okay, I got rid of the picture, sorry. Your book will use the script E. If you look at, this is a problem straight from your book. And I think, if I remember, the book uses script E for the power supply voltage. And then when I write script E, people, it's a new symbol, so I try not to use the script E too often. Yeah, and you're right, the field will assume it's constant, because if the field's not constant, that makes me, I don't want to deal with that problem if I make the field not constant. No, because the current's going to be going through the loop, right? I guess you can say, yeah, maybe I should be more careful. You know, you're right. Maybe I should be more careful in saying that the L is the distance between the rails. The reason why I extended it so it just, I don't know, generally people just extend it so you can actually see the end of the rod of this. Oh, let me look at your question. Sorry. My chat screen is off too far to the right. Just give me a second. Yes, the velocity would be different at any finite time, but it would be the same at infinite time. You're right about that. That's a terminal velocity. Now, you know, you're going to reach terminal velocity before that just because of the fact that you have friction, and then ignore that. I mean, even when you drop an object, in principle, you reach terminal velocity at infinite time, but you really don't. Or you can say, come close to it. I mean, if you're assuming ideal conditions, it will take an infinite amount of time for the velocity to reach terminal velocity. But yeah, it constantly changes until you go to t equals infinity. Assuming no friction. Now, the problem I have in the homework, problem 15 or 14, you have one of these rods on an incline plane. That one does have friction in it. It's really a 205 problem. But in that problem, I don't ask you for the velocity of function time. That would be too hard. Are there questions? Sure, no problem. Okay, so I guess you guys don't have any more questions. So I'm going to email you the practice test. So go over the homework problems. Go over the practice test. I might send you a fun one that I gave last semester on the final, just to play around with. Okay. So anyway, have a good weekend if I don't see you in 210R.